Hi guys, today we're going to talk about dehydration of alcohols. This is a really important reaction that alcohols can undergo. And basically, the way that you think about these types of reactions can be summarized by this rule named after a Russian chemist from the late 1800s. His name was Zaitsev. We'll get into his rule here in just a minute. But let's just show what a basic dehydration reaction would look like. So if I were to start with an alcohol, and I'll use cyclohexanol as my alcohol, if you treat this with an acid catalyst, so we're just going to write that as H plus catalyst, and heat. So often in chemistry we write this large delta sign for heat. Basically if you take an alcohol like this and add an acid catalyst, heat it up, what will happen is the OH group will come off and you'll introduce an alkene. So basically this OH group and one of the hydrogens that's adjacent to it basically comes off as water. Okay, so notice the two products then are the alkene and water. So this is why it's called a dehydration. We're kind of stripping water off of this molecule. Now the acid catalyst, what exactly is that? Well, the most common H plus catalyst is H2SO4 or sulfuric acid. You can use others. You can use HCl or phosphoric acid. Those acids aren't quite as strong though as H2SO4. And typically these reactions only require a drop or two of this for a fairly large volume of the alcohol. So when we say H plus catalyst, what we're really talking about is H2SO4. And as we know, when you put H2SO4 in water, this sets up an equilibrium to form hydronium plus HSO4 minus. So what's really happening then is the water is becoming hydronium, and we can then abbreviate hydronium as H+. So those, when we talk about H3O+ and H+, those are essentially equivalent. But for this reaction, the key is we do need to have this acid catalyst. And I'm going to show you sort of how this works in the next section of the video when we talk about the mechanism. So let me show you the mechanism of this reaction. A chemical mechanism is essentially a way for us to describe, sort of at the atomic level, what's happening in a reaction. So let me go back to this, this cyclohexanol example. And I'm going to draw out the lone pairs of electrons on this oxygen. So when you put in an acid catalyst, we'll just write it as H+. What can happen is the electrons on the alcohol, they act as a base. It's called a Lewis base in this case. They're going to sort of attach to this proton. And what that forms is now this. Okay, now notice that when oxygen has 3 bonds to it like this, it would then have a formal +1 charge. So we would write that with a plus charge there. Now just for clarity and continuing out the mechanism, I do want to just draw in a couple other things. I'm just going to put in the fact that our starting cyclohexanol has a hydrogen there, and I'm also going to just draw in the hydrogens here as well, just so that we can follow along what's going on a little bit easier. All right, so we've formed this initial complex now where we've sort of protonated the alcohol. And you can see now that this is essentially starting to look like water. Okay, but it's still attached to the carbon of the cyclohexanol. So what happens is that this bond now is quite weak. The carbon-oxygen bond is weak. And this is going to simply pull off of the carbon, so the 2 electrons in this bond are just going to be removed. And what that will do, it will now form a structure that's going to look like this. And as we do this, water is going to come off. So this is our water that's come off. And now look at that carbon there that was attached to the water. So when those 2 electrons are removed, what that's going to do, it's going to create this species here that we now have a carbon that's only got 3 bonds to it, and notice it's a plus charge. This is called a carbocation intermediate. Now that carbocation intermediate is a very fleeting intermediate. It doesn't hang around for very long. It's very reactive. And in order to now get our final product, which is going to be our alkene product, let me go ahead and draw the structure of that here. Okay, this is our final alkene product. Notice that something has to happen in getting from the carbocation intermediate to our alkene. Well, if you just follow the hydrogens here, notice that in this carbon there's actually 2 hydrogens. So one of these hydrogens is going to be pulled off, and the 2 electrons from that bond are going to swing down and form a double bond here. So what happens now is our water that was up here, I'll draw that here, it's going to abstract one of these protons, and it doesn't matter which one, it could be this one or that one, and the 2 electrons are now going to go down and form now this double bond. All right, and the byproduct is now H3O plus, or H plus catalyst. And that's why this is a catalyst. Once the H2O is converted into H3O plus, it can go back and act as a proton source to protonate other alcohols so they can undergo this reaction. So again, the overall process, or mechanism as we call it, involves protonation of the alcohol, the release of water to form a carbocation intermediate, and that carbocation intermediate gets deprotonated to now make our alkene product. And that is a very important part of this. Just always remember, when you're dehydrating an alcohol, the product is almost always going to be an alkene.